Good afternoon to all of you. Here present my pre-submission PhD. The PhD title is Design of Low Noise Amplifier for Multiple Bands and its Simulation-Based Performance Analysis under the guidance of Dr. So this is about the registration details and the paper published. So I have published around 10 papers. So 9 in the international journal and 1 is presented and published in IEEE college. So this work is in collaboration with the SM Wireless, it's a sister customer of RFIC USA. So part of work is completed at SM Wireless solution. So this is the outline of my PPT. That is, start with the introduction, then motivation of research, then problem statement, objective, then tools, result interpretation, conclusion, publication and references. So start with the introduction. The recent research in wireless communication has shifted to the multi-standards and multi-band application. So in wireless communication, there is a necessity of low. So I am designing one low noise amplifier. So and the application for it is from 500 megahertz to 6 gigahertz. So I can cover the many of the applications for low noise amplifiers for multiple band application. So these are the applications that can I cover, like advanced mobile phones service system that works on the frequency of 824 to 849 megahertz. Then global system, that is GSM. Then PCS system. So these are all applications can be covered with this low noise amplifier. So there are two technology, that is the gallium arsenide and CMOS technology. So the gallium arsenide is the industrial fluoride because it provides us a gain, better gain and noise figure. So I selected that one. So motivation for research based on literature survey and the paper review. So the need of our is to provide a fast communication with less distortion or less loss of signal. So the transceiver perform the main role in that, and we can design such a transceiver that can work for the multiple applications like WLAN, Wi-Fi, and the low noise amplifier is the main component in the transceiver. So with the help of that, we can minimize the noise and give us the better signal at the receiver. So this is about the objective of the research work. So that is the proposed work earlier. So I proposed this earlier, that is schematic and layout, and these are the parameters that I have decided with the help of the specification review and references. So the typical values are mentioned there, that is for gain, for low noise amplifier, that is 15 dB, 4 dB and greater than 1 dB. So what I have proposed earlier, that was greater than 15 dB gain. So and what I have achieved now, that is designed LNA, that is 30 dB gain. So then noise figure, that is typical value is 4 dB. So that I have earlier proposed, that is less than 4 dB, and what I have achieved, that is 2.3 dB. And the stability factor is greater than 1, and I have also achieved in greater than. Sorry.
Stability greater than 1 physically means.
Physically means it's means circuit is more stable. For
one is stable, more than 1 is stable.
More than 1.
Yeah, good.
And the frequency range, that earlier I have decided to 500 megahertz, so then I have achieved around 500 megahertz to 6 gigahertz, and the operating voltage is 3.3 volt. So I have reviewed the main papers for this, like 1 gigahertz to 4 gigahertz band. So the scope of work is to increase the operating frequency in increasing the gain. So everywhere I find that the gain is very low and need to improve the noise figure there. So this is the about the summary of work so that I have carried out. First one is the literature survey. Then I work on the matching structure because the matching structure is very much important to minimize the noise figure and to maximize the gain. So I have worked on the strip line structure. Then I have designed one LNA with the basic structure self biasing that is on the 2.4 gigahertz. Then I have designed the second LNA that is from works on the 1.7 to 2.7 gigahertz. Then design of another LNA that is 2.4 to 6 gigahertz, that is LNA 3. Then LNA 4 I have designed that is for the 500 megahertz to 6 gigahertz. So, and I have improved the performance of that LNA with the modification, with making the modification in the matching structure. I have used the strip line matching structure and I have done the comparative analysis also and the performance of analysis with the variation of the temperatures. So this is the methodology I have followed. First of all, I have designed some matching structure. I have worked on the matching structure, strip line matching structure. Then selection of the transistor, then selection of the biasing, then stability analysis, input output matching I have done. Then design of LNA with lump component and then design of LNA with strip line component, and then I have done the performance analysis of the low LNA. So the tools I have used, that is the ADS 2009, and the simulation I have done, that is S parameter simulation, stability check and HB simulation. So this is the strip line structure that I have worked. So these are the simulation results. So I have designed the strip line structure. So I have worked on the matching structure for 1.8 gigahertz, 2.7 gigahertz, then 3.6 gigahertz band, and this is the layout part of this. I have also tested this strip line structures, this matching structure in the lab on the spectrum analyzer, and I got the satisfactory result for that. So this is the LNA 1 I have designed. So the proposal of work is to design LNA for 500 megahertz to 6 gigahertz band. So preliminary work started with the LNA, the basic LNA design, LNA 1. So the gain is around 8.6 dB and the noise figure is 2.4 dB. That is not satisfactory, and there is a operating frequency is very low. So I have gone to the another design of LNA that is for 1.7 to 2.7 gigahertz. So where I have achieved 13 dB of gain. So they and 1.2 dB of noise figure. So the operating frequency also low. So I have decided to go for the another type of LNA with the another biasing structure. So I have designed the LNA 3 over there.
You are talking 1.8 volts?
Sorry?
1.8 volts supply?
3 volt, yeah. So that was for 1.8 volt. Yeah. So, but the results are not good for them. So, and the final one is for 500. And then another is the LNA 4, that is the 0.5 gigahertz to 6 gigahertz band. So where I have used the PHEMT transistor and the gallium arsenide process over there, and use the resistor divider because it gives us a high gain, low noise figure over there, and in negative feedback introduce the stability to the network. And I have used the strip line structure for the matching purpose because it gives us a ultra wideband application with the flatness. So this is about the negative, that is gives us a flat gain for ultra wideband and micro strip line structure. So two types of matching I have done to the LNA, that is input-output matching, that is required to get a good power at the load, and the interstage matching because I have designed the two-stage network, so there is the interstage matching with the LC component over there. So this is the 0.5 gigahertz to 6 gigahertz LNA, whereas I have done the input matching, then resistive biasing over there, negative feedback I have applied, then interstage biasing over there. So the results that I have obtained.
Here the voltage is 3.3 volt.
Yeah, 3.3 volt. Then the gain that I achieved around it's 26 dB of gain. Then the input and output return loss is near to the minus 10 dB. Then the noise figure that I achieved in for this circuit is 2.7 dB over there. Then I have designed with the improved circuit matching, that is the stripline structure I have used, and the gain I have achieved is around 30 dB of the gain for this LNA low noise amplifier that works on the 0.5 to 6 GHz. Then noise figure is also around less than 2.3 dB for overall band of 0.5 GHz to 6 GHz. And then input and output return loss is around minus 10 dB, and the stability is greater than 1 for overall band. And this is the comparison with the step by step. First LNA I have designed for 1.6 GHz to 2 GHz, and this is the gain I have achieved. So the final LNA that I have designed for 500 MHz to 6 GHz, so the gain obtained is 30 dB, and the gain flatness is less than 1 dB, and the noise figure is around 1.7 to 2.3 for the overall band of 0.5 to 6 GHz. So the noise figure is very important parameter for the designing of low noise amplifier. So this is the comparison with the research works earlier done. I have compared with the 2014 papers also. So the gain that I have achieved is 30 dB, whereas the others have achieved less than that. And the gain flatness is 1 dB, and the noise figure is also good. I am getting good compared to the others paper. So I have done the performance analysis for this circuitry also. So the scattering parameter I have tested with a variation of the temperature, SPO temperature variation I have done. So this is the gain variation that I have observed when I have changed the temperature over there. So 5 degrees Celsius I have changed, then 40, step by step I have changed 5, 30, 40, then 65 and 100. So this is the variation of the temperature that the gain and input is varying less than 1 dB here. So there is hence with change of temperature LNA, the performance LNA is remains same, the gain performance. Then I have checked with the input return loss also. So that is also changing with less than 1 dB. Then stability I have also checked the stability is greater than 1 for the overall performance of the 0.5 to 6 GHz. Then S22, that is output return loss, also I have checked. So and the noise figure. So noise figure is also not varying much, and it's less than 2.8 dB for all the temperatures. So this is the comparative chart. So whereas when we change the temperature like 30 degrees Celsius, 40 degrees, 65 degrees and 100 degrees Celsius, the gain not changing more than 1 dB. So the performance of the LNA is not changing with the more changing with the change of the temperature. I mean, it can work for the any temperature. And the noise figure is also not changing much because it is less than 2. The any temperature means it's step by step 30 degree, 40 degree, 65 degree and 100 degree. So I have done the LB simulation over there. I have provided input and output. So that is also not changing. So this is the final layout I have designed for this LNE. Then application wise, I have already explained that there are many applications I have covered with this. The conclusion is that in simulation based analysis, circuit is tested with a variation of the temperature of 5, 30, 40 and 65 and 100 degrees Celsius, whereas the gain is remaining the same for all frequency band and not changing more than 1 dB, means it can work on the worst condition also.
Given temperature, 5, 30, 40, 60, 100.
So it is in the simulation condition.
I know, in simulation. Because I am looking for real time scenario. What do you mean by that?
Means when we use the
I go to Kuwait, it is a 55 degree. It was. You mean that?
Yeah.
I go to Antarctica.
Yeah.
Low temperature doesn't work.
So for the low temperature it also work, but the thing is that whenever the circuit is operating,
are done with
higher side, because whenever the circuit is operating, It's
supposed to be working in Antarctica also.
Yes.
Needs where many electronic gadgets should work in Antarctica.
the thing is that
Lower temperature.
with increase in temperature, the performance of the any circuitry
But
gets changed.
simulation is okay.
Yeah.
We prefer to go on higher side.
Okay.
What happens if you go to the
Lower side.
lower? You know, in our scenario, Antarctica, what is the temperature?
It's lower side to manage.
It's okay. Because, you know, electronics should work there.
So circuit is stable for over the entire frequency. So the noise figure is also good for the with changing of the temperature. So results are compared with the referred papers and shows that the design is getting good gain and the good noise figure with the as compared to the earlier paper. This is over, and this is the letter I got from the. So these are the papers that I have published. And these are the references.
Tell me why only these? Anything else you can think of other than these two parameters?
I am designing the low noise amplifier, sir. So the noise figure is very much important.
Anything other than this? dB, and this line.
So the
other parameter.
so according to the this industrial standard, these are the parameter we consider.
It is new one.
So I have checked with the temperature also, means I have varied the temperature, I have checked the circuitry.
Now, how do I say that your LNA, in some other context, I say, right now you took the nice mineral, everybody uses. Can you think of something? Not for your thesis.
And the what I have designed, so that works for the multiple band applications. Means it can be used for the GSM. Yeah. So 6 gigahertz. So many of the applications are covered with this.
But the whole range it covers?
Yeah, whole range.
Performance wise.
Because the flatness is means similar kind of gain I am getting all over by the band.
Gain versus frequency.
See, when
so the 30 dB of gain, so that is not changing means 1 dB. 1 dB of change is there.
1.5 dB.
Yeah, very.
The whole range of 6.
Over range. So I can use for all the applications for that. So that is the different from the other selling.
There are questions? Where are our friends who have presented? They all left. I see very few. 1, 2.